So now we're going to have a little panel discussing the Robotics Mars Exploration Program. American Robotic Mars Exploration Program has had a string of successes since 2001, as well as some successes in the previous decade. It's gone through some changes. So we had first the big failure of Mars Observer, which was a program that took over a decade only to fail upon arrival at Mars. This inspired a change of thrust to go to the so-called faster, better, cheaper policy of Administrator Golden, and to send small, relatively cheap probes to Mars every 2 years, which then was implemented starting in 1996 with Pathfinder and Mars Global Surveyor, and then 2 failed probes in 1999, and then a success in Mars Odyssey in 2001, 2 rovers in 2003. Then we started to diverge from that a bit. We had the somewhat larger Mars Reconnaissance Orbiter program, which was successful, launching in 2005. A Discovery Mission Phoenix in 2007.
Mars Scout.
Yes, the Mars Scout program initiated by Scott Hubbard, and which program, though, by the way, we first advocated at our founding convention in '98 to have a discovery program for Mars, competitively chosen. But then there was, under O'Keefe, there was a significant change, which was Curiosity, which decisively moved away from the frequent small Mars probes to one large and expensive one. It was originally scheduled to launch in 2009. It did eventually launch in 2011. As we know, it did land successfully, but there was a lot of eggs in that one basket. So we went from $150 million Mars missions in '96 to Spirit and Opportunity, which were about $400 million each in 2003, and then Curiosity, which was about a $2.3 billion mission, landing in 2012. And now we have another Curiosity class rover, very similar to Curiosity, scheduled for 2020. So the missions have become less frequent. I should say that there was another Discovery mission made and launched last year, it will arrive this year, and another Discovery mission was chosen, InSight, which will go in 2016. Discovery missions are competitive missions. They're not part of some grand plan. They are individually bid competitively, university-led teams most typically, bidding against each other on the basis of science, cost, and competency of the design. And so we've had 2 Discovery missions make it into the program as well. But we moved to these large, in terms of the main line of the program, large, less frequent missions, more capable, but more risk in any one of them. And then, in particular, the current mission is oriented around the sample return. That is, notionally, the Mars 2020 rover, its primary mission is to gather samples and cache them and wait for the arrival of another lander, which will have a Mars ascent vehicle on it, and it will transfer the samples to them, and they will then go to orbit, where they will transfer samples to a solar electric-powered interplanetary vehicle, which will then transfer them to a point in interplanetary space where they will be retrieved from astronauts departing from the space station at L2.
What? I was with you. That's not the Academy's plan.
Okay, that certainly hasn't been advocated. That was the plan last year. But anyway, the part of that is sort of as Scott said, the part that's most official is the rover will gather the samples, an ascent vehicle will go and get the samples, and then it will go to Mars orbit, and it will transfer the samples to some other vehicle, which will return them somewhere.
It would be, that part of it is not that much different than what Stardust and Genesis have done. So,
All right.
what, I mean, finish your
All right, well,
monologue
anyway,
there.
okay, so, all right, so in any case, my real point is not to mock that particular plan, which was a year ago, the alleged plan, but that the focus clearly is on sample return. Okay. In terms of what the priority of the robotic program is, and a few rather expensive missions being coordinated together to execute the sample return as the primary thrust of the program. And for instance, as a result of its priority as a caching rover, the Mars 2020 rover, I believe, only has 28 kilograms of science instruments on it compared to about 80 on Curiosity. Because Curiosity could be, it had its payload fully dedicated to in situ science as opposed to caching. So, is this the right plan? Should we be doing a Mars program of relatively infrequent, relatively expensive, but more capable probes, A, and B, should they be focused around sample return as the primary objective? Okay, so that is really kind of what I'd like to bring into focus here and discuss. So, Scott, you have been involved in a lot of these planning groups and so forth. Why don't you talk about it?
Sure, and thanks for inviting me to spend some time with you. Let me go down to the fundamental for the robotic program, which is science return, or science return per dollar. I was on the National Academy steering group for the so-called decadal survey for planetary science. This process of surveying an entire scientific community and getting a consensus was started by the astronomers 50 years ago. They did the first one in 1960. And they were very successful in pulling together a consensus out of a large community of scientists who all have their own opinions. And by agreeing through the National Academy of Sciences process on their priorities, they have historically been able to get all of their priorities funded eventually by Congress. So across multiple administrations. So I'm talking about the great observatories, Hubble, Chandra, Fermi, Spitzer, those all came out of this decadal process. So in 2003, the planetary science community, which had been historically a quite fragmented bunch of people taking pot shots at each other, under the leadership of Wes Huntress, said we really need to adopt this decadal survey process. It's blessed by the National Academy of Sciences. You can find that is the gold standard of advice, scientific advice in this country. And rather than trying to kneecap the other guy, let's see if we can't come together under this umbrella and agree on what the priorities are, at least for the strategic missions, for the big guys, which you call the mainline program. So that was first done in 2003, and that was repeated then a few years ago, starting in 2009, and that was published in 2012. I was on this so-called steering committee that went through that entire process. What it involved was 300 white papers, 5 panels, a year and a half worth of work, thousands and thousands of person years, 1,700 unique authors on these white papers. And the 5 panels were divided by theme, more or less. Mars had its own panel, because Mars has always been a special place, going back many, many decades. So Mars, small bodies, outer planets, icy moons, Europa, for example, they all had panels. And within each of these panels, white papers were presented and hot debates took place as to what was the science that should come to the top. Within the Mars panel, led by Phil Christensen, it's a very, very well-known, very highly respected Mars scientist. What bubbled to the top was Mars sample return. They said this has been the holy grail for the Mars science community for a long, long time, and we now think that we can implement this with real knowledge. I killed, when I was the first NASA Mars czar in 2000, 2001, and constructed this architecture that we can come back to later if we want. There was a sample return mission on the table. And it was going to be done for $1.98, and it would involve, the French would build half of it, and all these other claims were made. And I looked at it, and in a room of about 90 scientists, mostly some engineers and other people, I said, who can tell me where to go that make it worth the expenditure of $3 billion for a half a kilogram of samples? Who can tell me? And I didn't get a crisp answer from anyone. There were advocates of the grab and go, but nobody could say at this point in 2000 that they knew where to go to find samples of such high scientific value that it was worth the expenditure of, then the estimate was $3 billion over multiple missions. So I said, we need to understand Mars as a system. We adopted the follow the water mantra, and it's been extremely successful. And part of doing this, understanding Mars as a system with multiple missions and an array of scientific investigations, was to find out where was that hot spot, the scientific place that was so compelling that samples returned from there would elevate our knowledge of the red planet in a huge step function, not incrementally. And so, having killed it then, I was a little bit, primarily because of the scientific risk. I said, in addition to that, you got your numbers all wrong. The technology challenges, I listed 4 or 5 of them, and budgetary challenges and so forth. But the principal thing was the scientific risk. Where are you going to go? Now, more than 10 years later, 14 years later, there was an NRC study that was before this decadal survey, and they said, we now think, so this is the science community, particularly the astrobiology community, that says the accumulated data of the last 10 years worth of missions is now so compelling, we think it's possible to select a site from which samples will elevate our knowledge of particularly the life question. Did life ever form on Mars? Are we alone? All that, at least ancient life. Would elevate this in a huge step function. It wouldn't be just another increment. So when the Mars panel came forward saying that it's scientifically the best thing we can do now to advance our understanding of habitability on Mars is to bring samples back, and I'll go into some more reasons in a minute, they were challenged by the steering committee. And I can't go into verbatim what happened because the way the Academy panels are structured, you're not allowed to quote directly out of that. But let's just say it was a heated discussion in which the Mars panel was challenged by everybody else around the table, which included the chairs of the other panels, as well as steering committee at-large members like myself. Are you really sure? Are you really sure? What if you can't get that? And they said, then forget it. Sample return or forget it. Adding incrementally more Spirit or Opportunity rovers will not advance the knowledge sufficiently that we are willing to go and put the imprimatur of the entire Mars community behind us. So they went all in, pushed all the chips on the table, sample return, or just forget Mars for this cycle. So that's what they brought to the table, along with the outer planets, say icy moons, bringing a Europa mission, and there's a Venus mission and an Icy Moons mission and so forth and so on. The job of the steering committee then, having received this, was to see what would rise to the top. And I give great credit to the co-chairs, the chairman, Steve Squires, well-known guy for Spirit and Opportunity, well-known planetary science, and his co-chair, Larry Soderblom, both very respected people. And the rest of us engaged in weeks of debate that was very intense, scientifically extremely pointed, and the reason people like myself were on there, as well as Tom Young and a few other folks, was to bring in the programmatic management, costing, budgetary realism that the first decadal survey did not have. Missions came out of that should not have emerged at the price tag they had. So in addition to all this scientific debate, we had an completely independent cost and technical evaluation by the Aerospace Corporation. And when they brought in the cost for some of these missions, the sticker shock knocked everybody flat. Because they weren't constrained like, advocates, no offense, advocates are optimistic, and they have to be. But these are people who said, historically you always, in this case, go to the next biggest launch vehicle, so we're going to add an extra booster on there. Sorry, but that's just historically how these prices go up. So the result of this was a very long debate about science per dollar, and in the end, I'll cut to the chase here, in the end, the strategic mission, meaning the big mission, that bubbled to the top for science value per dollar was the beginning of the Mars sample return mission. And we very consciously wrote, we realized we are starting a 3-mission sequence to get these samples and bring them back. But because of the life question, primarily, it's the first among equals of the science questions, we think that this is the thing to do. However, the mission that was brought forward by the advocates was costed at $3.5 million. And we said that is not doable with that kind of number. The budget picture was a little better back then. We said, if you can't bring it down to at least 2.5, then you should kill it and move to the next one. The next one was the Europa mission, which costed out at $4.7 billion. And we said, no way that this would blow the entire planetary budget for the next 10 years. It's scientifically compelling, but you need to go back to the showers and fix this one. Okay, so what's happened since then is that the original so-called MAX-C, Mars Astrobiology Explorer and Cacher, has become Mars 2020. Price tag is now at about $1.7 billion because of high heritage reuse of old Curiosity hardware. It has the Cacher, but that is consistent with the National Academy recommendation of the science value. The Europa mission, by the way, has come more than in half. I chaired the reviews of 3 Europa concepts, and one called the Clipper. I know this is the Mars Society, but I'll just tell you briefly about this. Very clever design. We said, this has to come in way cheaper than the all bells and whistles version. So they came in with this deep dip mission that reduced the radiation exposure to minimum, but still got the entire data set by the end of the mission. And that's been costed independently by aerospace at $2 billion. So I think the process has worked. That's a snapshot of how we got to where we are. And the all-in scientific nature of the Mars science community in sample return is going to yield the greatest increment in knowledge of the red planet.
I noticed on the program that it said the panelists for this was TBD, and I came in and I was thinking, I wonder who's going to be the panelists out here. And around noon, Bob asked if I'd be one of the panelists. So I didn't have a lot of time to prepare notes about this. I don't have the deep backgrounds that Bob or Scott have about this. The one thing I had thinking about this, we think about the robotic Mars exploration program as if it is a single monolithic one, and that is increasingly not the case. We do have a very, long-running and long-ranging into the future exploration program, but the United States is not the only country with an interest in exploring Mars. Europe has had a successful Mars orbiter, Mars Express. They are collaborating with the Russians on a program called ExoMars that will feature an orbiter in 2016 and a lander and rover in 2018. At least that's the current scheduled dates. There have been some rumors that ExoMars 2018 might become ExoMars 2020 because of some budget problems, and there's also the increasingly complicated geopolitical issues associated with collaborating with the Russians. Although, if you remember, not that long ago, ExoMars was going to be a European program with U.S. involvement. Until we backed out, we decided that we couldn't commit to that program, and we ended up going to the Russians. So that's one interesting program coming up in the future. India has their very first Mars mission en route, the very cleverly named Mars Orbiter mission. What was that movie? Mars Needs Mother, or something like that?
Mars Needs Women.
Well, there's one on its way. It's scheduled to arrive. It's actually within a few days of the arrival of NASA's Maven spacecraft. And there's already been discussion in India about doing a follow-on mission to make that mission successful. China, they were actually had a planned Mars mission as basically a secondary payload on Russia's Phobos route mission. That should be called the ill-fated Phobos route mission because it launched but failed to escape Earth orbit and re-entered several weeks later. They had a small probe that was going to hitch a ride and was on there. But China's increasingly talked about doing Mars exploration missions of their own, including perhaps doing a sample return mission of their own in the 2030 or so time frame. So fairly long term, but it's clear that you have, as the space capabilities of other nations grow, they're all showing interest in doing robotic Mars missions. So you've got, again, not just NASA, but Europe, Russia, India, China. Japan attempted a Mars orbiter mission a number of years ago, Nozomi, that suffered a number of technical malfunctions and ultimately failed to get into Mars orbit. They may try again at some point. And certainly other nations have expressed an interest in collaborating with these other nations by providing instruments or other expertise to these missions. So there's not a single robotic Mars exploration program, but there's really a multitude of programs out there. And that is certainly something to keep in mind about whether these increased international capabilities provide an opportunity for enhanced cooperation to do missions that might not be possible otherwise, and or do things less expensively than possible otherwise. So that's certainly something, an issue that hasn't always been on the table, but may become so in the future, particularly as the budgets of NASA and some other large space agencies become constrained. One other point I would make out is that all the discussion about these robotic Mars missions has been focused on science. We want to learn about Mars, we want to learn if it had life, does it have life, what were the conditions like there, all sorts of interesting scientific questions beyond the simple astrobiological ones that many of these missions probe. But if we're going to talk about human missions to Mars, be it in the 2030s or earlier or later, depending on which mission architecture and level of optimism that you have, we will also need some robotic precursor missions to test out some of the technologies needed. You might know that the Mars 2020 mission carries with it as one of its experiment payloads an ISRU experiment. Right. So you're already starting to see that. But it may make sense at some point to have sort of a bifurcation of the programs and have the continued science program but have missions that do test out high extreme technologies, that do the radiation exposure, to test whether you can do things like manipulate the regolith and turn them into blocks that might be great building blocks for future habitats and so on. Learning that with robotic missions before you start sending people to do that. And that's something that I don't think is really very high up on the radar screens at NASA or elsewhere beyond some of the experiments, for example, going on Mars 2020. But if you're really serious about sending humans to Mars, you're going to want to test out a lot of technologies that they'll need to be able to live and work and thrive on Mars before you actually send them there. So that's something to think about in terms of the long-term future of robotic Mars exploration. So while we talk today about the robotic Mars exploration program, if we do see a long-term future where we have humans eventually going, visiting, and even living definitely on Mars, we're going to need a multitude of robotic missions and robotic programs to make that possible.
So, somewhat in line with that, but a little more edgy.
I would expect nothing less.
Okay. I'd like to challenge all those committees. Okay. So, look, we've had this robotic Mars program in its current form since 1995 or so. Well, it's 1993.
Not actually completely true.
Well, if we take the Mars program as it has existed with its various permutations since the recovery from the Mars observer failure, which is sort of what initiated the current age of Mars. Yeah, Mars. Yes,
Could you talk
93.
closer to the mic, please?
Okay, with flight operations commencing in 95. Okay, and we take the 20-year period from the launch of Pathfinder and NGS through the arrival of Maven, and this is a certain period of time. And I mean, there certainly have been changes in policy over this period of time, but nevertheless, we take this span with its variety of missions, a number of small missions, one big mission, Curiosity, medium mission, the Spirit opportunity in Mars Reconnaissance Orbiter, the couple of failures, but mostly successful. Okay, I mean, this has been a tremendously productive period of Mars exploration. A large number of missions, kind of a spectrum, lots of small ones, a few medium ones, one big one. In my view, a balanced program. And although one could argue that this other mission instead of this mission, but still, take it. It's been tremendous. And now we're going in a different direction, where we're proposing to spend, well, at least 10 years on this sample return project, possibly significantly longer. And except for discovery missions, which sort of got into the program sideways, that's what the program's going to be doing. And I wonder if in focusing on this goal that we're not impoverishing the program and also introducing a very high level of risk into the program. And there's a lot of things that one could do on Mars aside from return a sample. Okay? And there's a lot of things. I mean, I think that the question you asked to those scientists that day in Scott could still be asked. And if we're talking about looking for life, are we really going to expect to find life or evidence of life in a few kilograms of samples collected from one small region of Mars? The rover can move, sure, but it's all going to be samples collected within some tens of kilometers of each other, as opposed to this vast planet. And if we're looking for life, and I'm a big fan of looking for life, you could look for fossils. You could look for signatures of life, such as biogenic methane. You could attempt a direct life attempt detection experiments on a Viking, or you could drill and try to get to subsurface water and look for extant life, okay? And there's an awful lot of places, or you could look for frozen remains of life in polar situations, okay? So there's a lot of places to go and a lot of things to do. And so, for example, okay, I mean, the most obvious counter program might be that, you know, instead of doing this, launching 2 NER rovers to Mars every 2 years, and you have, you know, 12 of them over the same period of time, and you'd be in 12 different places, and they'd be instrumented in 12 different ways. And you do all kinds of stuff. You might have a chance of finding fossils on the surface with so many rovers in so many places. You could send them with methane detection equipment to places where the suspected vents are. You could, or alleged, whatever, putative, call it what you will. You could send them to frozen places, you know, and try to find out what's in there, preserved and frozen. You can have life detection experiments. We're going to do other things than rovers. We can have drills, including you know, the mole on the wire that can go down much deeper than a conventional drill and try to see what's in the groundwater. You could have other kinds of vehicles that are much faster than rovers. Balloons, for example, carrying ground-penetrating radar. You know, the strength of the radar signal goes up as the inverse fourth power of the distance. So an aircraft that is 1 kilometer or 3 kilometers above the surface can get 1,000,000 times the radar return as a satellite on orbit. You know, there's other instruments that, I mean, the scientific community is filled with people with ingenious instruments of one kind or another that they would like to fly to Mars. And if we had a more varied program, a more balanced program, with lots of small missions, as well as some flagships. I mean, I'm not saying anything that new. NASA's philosophy over time has been a mix of flagship and smaller missions. That this might indeed be better and more productive, and also not place us in the position of putting so many eggs in one basket. I wonder if a sample is really going to be definitive in terms of the search for life on Mars, and that a broader search and a broader and more varied approach might be better. Also, there's other things. You know, for instance, yes, the Mars 2020 rover is going to have one ISRU experiment of zirconia cells dissociating CO2 from oxygen. But with a rover, you could also sample the soil, extract water from the soil, and use that water plus the CO2 and produce methane and oxygen by a symbiotic electrolysis process. But aside from the 2020 rover, there is no opportunity for doing that over the next foreseeable future because that rover, you know, the program has been so narrow that there's all kinds of things that we would like to do that can't be done.
So, unlike Cheng Diaz, I'm here. I enjoyed this, Bob.
And I invited him on the podium for exactly that reason.
So let me respond if I can remember I mean, you brought up a lot of issues. Let me say at the very beginning, this is a good discussion to have.
Yeah.
That just about everything you rattled off in your to-do list was in one or the other of these 300 white papers. So balloons, multiple rovers, a program for Mars consisting of only small rovers, all those things were brought to the table, presented by an advocate. I sat in on some of those sessions. The people on the steering committee were encouraged to come to the panel sessions and to see what was going on. And in the end, the power at this time of bringing back a sample, which has been around since since at least Viking. And this sample return is something that has been on the planetary science table to-do list near the top for 40 years. And let me just try to give you a couple of reasons why that happened. First of all, let's remind everybody that originally, when I was asked by Goldman and Dan and Ed Weiler to be the first Mars program director after the 2 failures, there was a single Mars program that was, at that point, about $400 million a year. And then in my negotiations with ONB, we got a Christmas present of an extra $100 million a year for 5 years, so we got it up to over $500 million. Since that time, it crept up a little more, and then it's been really quite devastated, and it's gone through this horrible sawtooth where, it was almost out of business. It came back to life. In 2012, truth be told, don't tell anybody outside this room, ONB was on a path to kill the Mars program, to zero it out, okay? Because they figured that nobody would push back. Well, the community did push back, and it's now slowly regaining its health. Yeah, thank you all. Without the Mars Society, the Geophysical Union, the Planetary Society, and all the people out there who sent in those important letters and phone calls, the program would not be on its way back.
Scott and I did a seminar together on Capitol Hill at that time as part of that pushback.
Right, and so congratulate yourselves for having saved what I think is one of the crown jewels of the U.S., certainly U.S.-based program. And in 2003, the first decadal survey, Mars had its own survey. It was able to be considered by itself with strategic missions, middle-sized missions, and the Mars Scout program, which was a competitive, bring your best ideas and the best idea will win. That got pushed into, first of all, the Scout program was killed, and they said, well, we'll open up discovery to Mars, and it's been successful. InSight is an example. When this last decadal survey was done, Mars was pushed in there without any special cachet. It had to make its case against Europa, Neptune, Venus, everybody else. So the landscape shifted in which the Mars program had to operate. The planetary science portfolio is still very broadly based. There's the strategic mission, which is Mars 2020. There is, if the current budget holds, if the House and the Senate agree on their numbers, there will be a New Frontiers, probably 2 New Frontiers missions over the next 6 or 7 years. And then they're trying to get back to a cadence of a discovery mission, every 3 years or so. Right now it's about every 4 years. So the portfolio for all of planetary is still fairly diverse. The reason that I think the Mars community went all in, and as I said, the ideas you brought up, which are terrific ideas, and if money was no object, you'd do them all. But the reason that sample return is that after more than a decade's worth of investigation, Pathfinder was a demonstration of technology. A little bit of science came out, but not a great deal. Then beginning, though, with Mars Global Surveyor, Spirit Doctrine, Odyssey, Spirit Doctrine, and so forth, the science community concluded that as a result of the increasing capability, they now were really getting a handle on Mars as a system. And as I said a while ago, there was an NRC study around selecting a sample, because it was the astrobiology community that pushed back hardest on going for a sample back in 2000. They said, we're not ready. The hard rock geologists would be happy, but people want to understand habitability. And so now I'm turning to the question of looking for life. Okay? The plan that the Mars program is executing for Mars 2020 and as part of a sample return campaign is habitable environments, the fingerprints of life, and that means ancient life. So presence of organics, complex carbon compounds, environments that would have been habitable. In fact, Curiosity, I think, has now got the slam dunk that they found in the first part of that mission, the habitable environment. And so that's what this is looking for. If you saw a microfossil, that would be terrific, but they're really looking for habitable environments, organic compounds, and the signatures, if you will, that the community, and I appreciated Gil Evans, Terry Gil Evans' son, the community has never completely embraced that finding as seeing life on Mars. I think everybody here knows that. And that was primarily because there was no associated organic materials, organic compounds detected. They said, how could this be? And that's where the whole idea of a very oxidizing surface peroxide came from. So that's what the sample return is intended to do. And let me just, before I hand the microphone back, mention 3 or 4 things that sample return brings you that no amount of in situ investigation can. One is the number and type of instruments. Okay? There are some types of things like absolute chronology that at present, I don't know of anybody that's got a good technique. There are some proposals out there, but if you need to accelerate and look at the decay, you can put in a sample in an accelerator, look at the decay times to get absolute how long ago was the sample was created. Then you need instruments on Earth. You have all the laboratories you can possibly take advantage of. When you select the instruments that go to the surface for in situ investigation, you're fixing that. And you're fixing that with a number of investigators as well. And finally, as we've seen with the lunar samples, you can follow the pathways of discovery. People are still finding out interesting things from the half a ton of moon rocks that the Apollo program brought back all those years ago. And having samples here is a mechanism to even revisit much later things that you may have not known or with new instruments. So in addition to the other scientific arguments, those kinds of arguments were what I think convinced the entire steering committee, which remember included the chairs of the other bodies. And the Europa people had to agree with this, and the Neptune people agreed to this, and the Venus people agreed to this. That's why sample return became, beginning with 2020, the top of the heap for the strategic mission. So I hope that responds in some way to the kinds of issues you brought up. Jeff?
You're in the middle here.
I know, I'm just up here for my good looks, I guess.
And your chart.
And my chart, absolutely. I'll just touch on a couple of things here. Scott alluded to sort of what you might call the budget shenanigans with the planetary science program over the last few years. The planetary science program at NASA had, prior to a couple of years ago, been about $1.5 billion a year line, and then the administration proposed cutting that by 20% down to $1.2 billion, and so that's led to budget fights over the last couple of years with the planetary science community fighting to get that funding restored and getting at least partially restored, thanks to some advocates in Congress to do that. But that's led to a lot of debates within the planetary science community about, should we be spending all this money on something like Mars 2020? What about Europa? What about some of the other exciting destinations in the solar system, like Titan and Enceladus, and other places like that? I know a lot of people in the planetary science community were a little upset when a Mars mission won the Discovery, the most recent Discovery competition a couple of years ago, the InSight lander, because that was, again, as previously mentioned, competed among various programs, and InSight was one of the 3 finalists. One was a comet mission, and the other was a mission to go to Titan and actually float on the lakes of liquid hydrocarbons on Titan's surface. And those missions lost out, and a lot of the planetary science community was sort of miffed that Mars was going and stealing their lunch money, so to speak, by taking money out of the Discovery program, which is programs like that. But so there's a lot of debate about that, and I don't think that's necessarily even as the Mars 2020 program picks up steam and we set sort of this the ground for future sample return and so on, that those debates are going to go away anytime soon, because budgets are going to continue to be constrained for the foreseeable future. If I had $1 for every time someone said flat is the new up, I think we probably could afford a Discovery class mission at this point in time. Referring to flat being the new up, being a reference to being fortunate that your budget isn't being cut and that it's being held flat. So that's something to keep in mind. And basically one other thing as we talk about Mars exploration programs in general is one big question that those interested in Mars exploration, whether they are planetary scientists or human exploration advocates, seem to ask is, what is really the ultimate purpose of a robotic Mars exploration program? Is it primarily or entirely scientific to help unravel the mysteries of the red planet, to understand whether it might have once had or still has today life, or simply to understand how it formed as a part of better understanding the solar system that we live in? Or is it to set the stage, is it to really be a precursor for eventual human missions? If you're sitting in this room at 8:50 p.m. on a Friday evening, you're probably interested in human exploration of Mars. Ultimately, that's a question that we have to ask. Are we pursuing Mars exploration solely out of scientific curiosity, or are we setting the stage for future exploration? And I think really fundamentally, given the emphasis that we put into Mars, I think a lot of people, even though they may not go out and overtly say it, they're interested in sending these robotic missions to Mars because one day they hope to go to Mars, or be able to send people to go to Mars. A lot of the geologists and other scientists who work on these missions would love to go themselves. They can't right now, so the missions become their proxies for doing so. But they'd like to go for scientific purposes. There are other people who like to go for other purposes. How do we fold that into a long-range strategy for human and robotic Mars exploration that takes into account the budget situation and the capabilities that exist outside of NASA and outside the U.S. to enable something like that? Those are big questions that don't typically get asked a lot when you're talking about what instruments to put on the 2020 Mars rover or how to best do a sample return mission. But they're pretty critical questions in the long term that need to be addressed in one way or another.
So, yeah, I'm going to continue a little. There's significant questions to my mind as to whether sample return is the best way to do sample return. Because if we say we want to get samples back from Mars, how did we get samples back